For this week video lecture, we're going to discuss about time response of first order systems. So there's two components. First one is we're going to look at what time response is. So time response, we have actually seen it in previous chapter, in chapter number 2, before we get into Laplace transfer, introducing what Laplace transform is. We have introduced what time response is, but now instead of using the usual method to find the time response, we're going to use another easier method, and this chapter will be specifically dedicated for first order system, right? So at the end of this, you should be able to determine the time response of first order control system using, well, the easier method is, now there's the clue here is using what we call poles and zeros, right? So before we goes to the definition of poles and zeros, because that's the thing that is new that we're going to learn in this chapter. First of all, let's go back to time response and look at the definition of time response. So what is the time response of a control system? Time response is basically the time solution to differential equation. So imagine having your FBD previously in different exercises of having different mechanical system. When you have differential equation, you have two options, right? Basically, if you have differential equation, let me change into a pen. So what you do is, when you have a system, you usually do your FBD to create to look for the relation between output and input, right? And the relation between output and input are written as basically as a differential equation. So differential equation, for example, relates between speed, which is the output, and it relates it with your input, which might be a force, right? So in order to find time response, finding time response means solving this differential equation. And looking at that, basically at the end, when we solve the differential equation, we will end up with a graph as a function of time. What is versus of time? Of course, we will have the output versus of time, versus time. So the output could be here, as I mentioned, is an output of speed. We could have a different type of output. It could be speed. It could be as well a position or acceleration or any parameters that could be seen as an output. So that's what the time response is. And then when we look closer into a time response basically can be divided into two parts. And this has also been seen in the first chapter. The first one is what we call natural response, and the second one is what we call forced response. So let's look into more detail about it. So what is natural response? So in terms of textbook definition, natural response is caused by the system itself. The system means it's caused by the parameter of the system. So imagine if you have, for example, a system of damper mass system, right? Damper mass system. If you have a spring mass system, for example, this natural response is caused by the system. Caused by the system means it depends on the parameter of the system, which is, for example, in this system it will be depending on M and K. So the time response, there is two portions. The natural response, so the natural response is basically this part. This natural response will depend on these parameters, the parameters of the system. So for example, if your system have more parameters, not just M and K, for example, M, spring K and damper B, for example, then it will depend on those parameters. It means that if you change your parameters M and K, it will change the form of your time response in this part, right? And then the second one is the second portion, this last portion, the steady state response. That's what we call steady state response. Is also known as forced response. Why is it known as forced response? It's known as forced response because it is influenced by the input. For example, if you put an input of step of a certain magnitude, the amplitude of this value of the steady state response depend on the input. The higher the input value, then the amplitude or the height or the amplitude of the steady state response will increase. If you have less input, then the value, the amplitude of the steady state response become lower, right? So if we look at it in terms of the graphic representation of the graph, so here we have basically a time response of an elevator. So it's an example we've seen in the first chapter. So we have the first part, which we call transient response. Transient means it keeps on changing. Transient response is also known as natural response, which is caused by the system, depends on the parameter of the system, be it M, K, or B, right? Or friction and so on and so forth. And then the second part is what we call steady state response. This is caused by the input that we put into it, right? And then there are, of course, when we look into time response, there are several criteria of performance: steady state error, steady state error, and then there will be the time of response that we will also look into it at towards the end of this lecture. So how to obtain a time response? So I'm going to go very quickly here. So the usual method that we use is, so now this is the method that we've been using previously. What we do is, the first step, you have the schematic. So imagine you have the system, you have to represent it in a schematic form. For example, this is a mass spring system. Once you have the schematic form, then what you do is you identify the forces reacting on your system, and then you write down your FBD. With your FBD, you will end up with differential equation. So once you have differential equation, you have two choices: either solve the differential equation, then you find directly the time response, or for example, in this case, is a very simple differential equation. You can of course solve it directly and find the time response. But usually the system is not as simple as this one. So what would you have is, basically you have a much complex differential equation that are not that cannot be easily solved using ordinary differential equation method. So what we do is the thing that we have done in second chapter, which is transform it into a frequential domain using Laplace transform. And we've seen, if we have Laplace transform, then we can always we can therefore write a transfer function of the system. So the transfer function, again, if I have to remind you, transfer function is the output over the input. So this is transfer function, right? So if you go back here, for example, here you would have a certain input put into it, and the value of the steady state depends on the input. So the black graph is basically the input, and then this part, this transient part, will depends on the value of M, K, M and K, for example, right? So if you change M, then the M and K, then the form of the transient response will change as well. So now the question is, why do we use transfer function? If you look here, if someone can solve differential equation, they might as well solve differential equation. But why do we use transfer function? There is a very important trick that we can do with transfer function, which is we'll see in the next part. So transfer function allow us to do two things. It allow us to do two things that cannot be done with differential equation. Of course, transfer function and differential equation can lead us to the exact equation of time response, but transfer function also allow us to what we say, to evaluate even before completely solving the differential equation. We can evaluate the response before completing the whole steps of the exercise, right? So it allows us two things. We says that it allows us to have a solution by inspection. So we'll see what solution by inspection means, and it will allow us using solution by inspection. It will give us a qualitative solution. What does it mean to have a qualitative solution? Having qualitative solution means we can directly know, for example, basically whether in transient form, how will be the transient form, for example, in terms of steady state response, at which level the steady state response will be, right? So that's qualitative. It's not quantitative, it's just qualitative by looking at equation. So how do we do this solution by inspection and qualitative solution? So in order to do so, the easier method is basically to use poles. So what we call poles. So now we have to look at what's the definition of poles. So what is poles? In order to look at it, let's take an example of a transfer function. So let's see, now we have a transfer function over here that's written as there is a numerator and denominator, so it's s plus 2 over s plus 5. The transfer function is called gs, and we have an input rs and output of cs. So rs now is 1 over s, so I'll explain in the coming slides what this input means. But now what we need to know is how to find the poles. What's the definition of poles, right? So the poles, in order to find the poles, we need to look at the transfer function gs. So there's not just poles, there's another term as well. It's poles and zeros. So let's take a look at what are poles and zeros. So what are poles? There are rules that you have to follow in order to identify poles. So the first rule is poles is the value of Laplace transform variable s that cause the transfer function to become infinite. So we have a transfer function gs. The value of s, if you replace s with a certain value, the value that make the transfer function become infinite, that value of s is what we call poles, right? And then there are second rules. It's not just that the value of s of that poles will make the transfer function become infinite. Any roots of the denominator, so second rule, any roots of the denominator of the transfer function that are common to the roots of numerator. So if you have any roots of the denominator of the transfer function that are common to the roots of the numerator, they are also poles. So what does this mean? It means that, imagine you have numerator and denominator. So let's see if I have a pen. So it's always denominator over is numerator over denominator s, right? So you might have, for example, on top, so you have a certain equation here, but at the front you have it is multiplied by, for example, s plus 1, and at the bottom is also multiplied by s plus 1. So in algebra, the tendency that you have when you have s plus 1 over s plus 1 is that you want to cancel it out. If you cancel it out, it means you lose the information of poles and zeros here. You lose the information of poles and zeros here. So in transfer function, you have s plus 1, so the same function on top and at the bottom on numerator and denominator. You don't cancel them out, you keep them, and s, so here s, so basically s equals to 1 minus 1 is also a poles for this system. Why? Because if you put s equal to minus 1, then this will become 0. When this is become 0, then the whole transfer function will tend towards infinity, right? So we'll look into example later to understand this more. Okay, transfer function. Let's take a look at this. This is an example here. So if we have a transfer function of s plus 3 over s plus 5 multiply s plus 2 multiply s plus 3, so the first rule says that the transfer function, the poles is basically the value of s, where if we replace that s with that value, then the transfer function will become infinite. So to make gs infinite, we have to make the denominator become 0. So in order to make it 0, we have to make, for example, for this part of equation, we have to make s equals to minus 5. Here s, it will be 0 if s equals to minus 2, and here it will be 0 as well if s equals to minus 3. So minus 5, minus 2, and minus 3 are what we call poles. So minus 5, minus 2, and minus 3 are poles of this function gs. Okay, so next. The next thing is that we have to apply the second rules as well. Second rule says if you have on the numerator and denominator the same function, the same value, then that value of, for example here, -3 is also the poles of the system. You don't cancel out s plus 3. You don't cancel out s plus 3. Where if you do it, then you will lose the information. We'll lose one poles. We need the information of all poles, because this will help us in identifying the time response later, right? So you don't cancel it out. Okay, so next we're going to see is what is zeros. So zeros is the same thing. There are two rules. The first rule is so it is the opposite of poles. If poles is the value of s that caused the system to become infinite, now is the value of s that makes the transfer function becomes 0, right? So in order to make it 0, now you understand, to make it 0, the numerator of the transfer function have to be 0. Second rule is the same rules. You have numerator and denominator the same function, the same value, then you don't cancel them out. So let's take a look at an example. So here again, for the same transfer function gs of s plus 3 over s plus 5, s plus 2, s plus 3, the thing, the value of s that will make the transfer function becomes 0 is, in order to do so, we have to make the numerator become 0, because 0 over any number will becomes 0, right? So to make this 0, s need to be equals to minus 3. So at minus 3, s equal to minus 3 is the zeros of this transfer function. And of course, the second rules apply. You cannot cancel out s plus 3, because if you cancel out s plus 3, then you lose the information of poles and zeros, right? So I think now it's clear on definition. So this has to be clear, because every time we have a transfer function, in order to do anything in automatic control system, you have to identify the poles and the zeros. Okay, so let's take a look at another example. Right, so for example, I think we can go quickly through this. So here, what are the poles? The poles are basically -1, -1, and -3. -1, -1, and -3. If there are double -1, we say that there are two poles that are at the same position of -1. We don't say that there's only -1 and -3. There are, in fact, -1, -1, and -3. So the 0 here is -7. This is easy to understand. And now here, here, what are the poles? Poles are -11, -2, and -9. And for zeros, the zeros are -13 and -3, right? So I think you get the idea, the concept of poles and zero in a transfer function. So now that we know the definition of poles and zeros, we're going to use it in order to come out with time response by inspection. So how do we do that? So the first thing to do is, of course, to find out what is the so how to obtain the time response. The first step is to find, just like in no, we haven't done this. So how to obtain the time response? The first thing that you need to do is to find the output. So now the output is Cs, and knowing the properties of transfer function, we know that Cs is basically the product of Rs and Gs. Once you do the second step, so I'll just brief the steps, and then we'll look at the example on how to do it. So once you have that, for example, here it will be 1 over s multiplied by s plus 2 over s plus 5. Once you do that, what you need to do is we need to find an inverse Laplace of it. So finding an inverse Laplace of 1 over s multiplied by s plus 2 over s plus 5, if you refer back to your Laplace transform table, there's no such function. So in order to do so, you have to separate them into different fractions. So you need to expand the transfer function using partial fraction expansion technique. So once you've separated them into different fraction, you can perform the inverse Laplace transform. So before we start, before we're going to be able to do the inverse Laplace transform, basically before we were able to find the output, as we know, the output is basically the product. So here the output is the product of the transfer function with the input. So the thing that we know that we need to know first is what is the input RS. So what is the input RS? So for example, if you go back to the exercises that we had in chapter 2, where we have to define different transfer function, the input could be force, right? Most of them, the input are force, and the force can varies. The type of force, the type of input can varies. So there are different type of input, and the RS will depend on this type of input. So here is written 1 over S. Let's see what is 1 over S. So there are for this course in particular, we will treat different input, but the most usual inputs are these 3 types of input. So the first one is what we call a step function, a step input. What does it mean, step input? It means that at the starting times, for example, t equals to 0, we put a constant force at value. For example, here is noted as y equals to 3. So this is what we call as input force or step input. For step input in time domain, the value is just the constant a. For example, a is this constant, which is now is equals to y. It's also called y, which is equals to 3. So RT, for example, for this, RT equals to 3. So a is this constant, right? And the problem is this is a writing in time domain, but your input RS for the transfer function need to be written in frequential domain. So in frequential domain, in Laplace transform, is if you look the Laplace transform for a constant, then you'll find that the Laplace transform for a constant is basically the constant multiplied by 1 over S, right? So if the force, the constant step input force is 1, then it's 1 over S. But now we write it as A over S because it could have any value of constant of A over S. So the next one is what we call ramp input. So the ramp input is the second one. It means it's a continuous, gradually increasing input force, for example, in our mechanical system. And in time domain, it's written as AT. So A is the gradient on which the input is increased. If we find the Laplace transform of AT, the Laplace transform of it in frequential domain is A over S squared. And for the last one, it is basically what we call a sine input. So if you have an input of oscillating force that you put onto your system, so an oscillating force can be written as A. A is the amplitude or the peak of your sine wave, A sinus omega t, with omega the pulsation, which is 2 pi. Omega is 2 pi multiplied by the frequency, so frequency of the sine wave. And in Laplace transform, in frequential domain, a sine wave can be written as A over S squared plus omega squared, right? So depending on the input, you need to write RS accordingly. So let's see how do we obtain the time response for this particular transfer function of S plus 2 over S plus 5. So let's say we have an input of 1 over S. So if you remember, what is 1 over S? 1 over S means that we are actually having an input of a step. So it's a step input with an amplitude of 1, right? So it's A over S, and now A is equal to 1, so it's a step of 1. In fractional domain, it's 1 over S. So the first step is to identify it, so it's 1 over S, and the next step, second step, is to find the output CS. So CS is the transfer function multiplied by the input, so it's 1 over S multiplied by S plus 2 over S plus 5. So the next thing that you need to do, so these are the things that we have done before, is to do partial fraction. So I'll not explain partial fraction furthermore in this lecture. So you do your partial fraction in order to be able to do inverse Laplace, right? So this is stuff on partial fraction. So we find at the end that CS equals to 2 over 5 over S plus 3 over 5 over S plus 5. So now we have the output of our system written in partial fraction, right? So now that we have this form written in different fraction, separated fraction, we can directly find, for example, 1 over s, the inverse Laplace of 1 over s. So the inverse Laplace of 1 over s is basically a constant. So inverse Laplace transform of 2 over 5 over s is the constant 2 over 5. And the inverse Laplace of 3 over 5 over s plus 5, if you look into the Laplace transform table, so please refer to your Laplace transform table. If you find 1 over s plus a, the inverse Laplace is basically exponential minus at, right? Exponential minus at. So the inverse Laplace of 3 over 5 over s plus 5 is 3 over 5, which is the constant, multiplied by the exponential or exponent of minus 5t. So now in usual methods, so this is a usual method that you've done previously. In usual method, we found therefore the time response. So this is the time response of our transfer function that is submitted to an input of step input force, right? So we end up with Ct equals to 2 over 5 plus 3 over 5 exponential minus 5t. So this is our time response. Now with that time response that we have calculated, we can plot a graph. So basically here in yellow is your input which is a step of 1. So at time 0 it increased to 1 and it stays constantly at 1. And then in purple is our time response, which is 3 over 5 plus 3 over 5 minus exponential minus t, right? So you can trace it, plot it using MATLAB, of course, or you can even try to plot it, try to evaluate it by finding the value at t equals to 0 and finding the limit when t tends toward infinity. You'll find the same sort of graph. Now in this slide we can see that there are two portions of the graph. So basically there are this 2 over 5 over s and there's 3 over 5 over s plus 5. So how do we relate this to the poles and zeros, the poles and zeros position? So this 2 over 5 over s, when we inverse Laplace it, we get a constant of 2 over 5. So this constant of 2 over 5 define basically our force response. It define our force response, which is the steady state that we have at the end. Whereas this 3 over 5 over s plus 5, this determine our natural response or the transient response. Why? Because in this part we have the exponential part. This is the part that define the curvature of our transient response, right? This define the curvature of our transient response. So if we look into point by point in terms of what does it contribute in terms of input poles, system 0 and system poles. So input poles, just now what do we have in poles? In poles what we have basically is 1 over s. Input. We have a step input 1 over s. So this comes basically from the input. This is an image of the input. So what we can do is we can plot. So this is something that you also need to know, plotting the position of poles and zeros on S-plane. I will explain it in a separate video on plotting the poles and zeros. So if you have poles, usually you mark it with X on S-plane. If you have zeros, you mark it with a circle or zeros, right? And what is S-plane? S-plane is basically an XY graph, where in X you have what we call sigma. I'll explain later what sigma is. And in Y-axis, j omega. So for example, our numbers here, the poles that we have for this transfer function is s plus 2 over s plus 5. So the poles are real number, so they will be placed on the real axis, because j omega is basically, looking at j, you have a clue that this is an axis of a complex number. But our zeros and our poles are all real number, they are not complex number, so they are just situated in this sigma axis. So for example, let's look at the input. Input is 1 over s, right? So if we look at the function of 1 over s, the poles is equals to 0, because, right, 1 over s, the thing that make 1 over s infinity is when s equal to 0. So the pole of our input is at 0. What about the system? So the system also influence this part, 2 over 5 and 3 over 5 plus over s plus 5. So the zeros of our system, the numerator of the transfer function was s plus 2. So the 0 is minus 2. So we can plot it's minus 2. And as for poles, the poles is at minus 5. So we can plot it as cross at minus 5. So if we look into its influence, we can say that input poles generate force response. So input poles, this part, generate what we call force response. What about system poles? System poles, it generates transient or natural response. System poles generates natural response in the form of what appears here as exponential minus AT, minus 5t here. And both zeros and poles of the systems generate the amplitude of time response. So it influences on the amplitude as well, right? So in previous slide, what we have seen was we did find the time response using usual method, which is finding the Laplace, going through all the steps of doing partial fraction, finding the inverse Laplace transform, and then goes back goes back into time response. So now let's see how do we do it by inspection. So it's basically we're going to jump several steps to be able to evaluate preliminarily, I would say, do it fastly without going through all the steps, right? So to do so, we'll have a look at a bit more complex system. So let's say we have a system of s plus 3 over s plus 2, s plus 4, s plus 5. As you can imagine, so now our system is not a first order system anymore, because the number of poles, so this is something that we haven't discussed about, but if you look into previous transfer function, it was s plus 2 over s plus 5. So the poles, the number of poles, we have only one poles at minus 5, right? So having one poles means we have a first order transfer function, a first order system. But now here, of course, it's not a first order system, but it is here in this chapter just to illustrate how easy it is using the what we call the identification or qualitative evaluation method to predict the response, the time response of a system, right? So that's why we pick a much more complex transfer function. So this is the transfer function. We have the same input of a step 1 over s. By now I think you should know this. So what do we do? First, we have to identify, to do it, to evaluate the time response of the transfer function by inspection. By inspection. What we need to do first is to identify what the poles and the zeros. So the poles are, you can see it is equals to minus 2, minus 4, and minus 5, and the 0 is at minus 3. So by inspection, by inspection, what is it by inspection? By inspection, we know that if we multiply 1 over s with the transfer function, at the denominator, we will have a product of s multiplied by s plus 2, multiplied by s plus 4, multiplied by s plus 5. And we know from previous method, what will we do in the next step is to separate the fractions using partial fraction. So if we separate them, we will have the fraction separated, and we'll have at the top the value of the coefficient of that fraction, right? So now we will not calculate it directly, right? Because we just want to evaluate it by inspection. We just want to inspect it. We suppose that the value is k1 over s. The fractions are k1 over s. Of course, if you do partial fraction, you can find the value of k1, k2, k3, and k4. But for now, we'll leave it as k1, k2, k3, k4. So by inspection, we know already that it will be equals to k1 over s plus k2 over s plus 2 plus k3 over s plus 4 plus k4 over s plus 5. So using the properties that we've seen in previous slide, we know that the 1 over s come from the input. right? Because that's the product of 1 over s with the transfer function. So this will give us the forced response, which is the steady state part. And then we have this whole part which will give us the natural response. Why do we know that it will give a natural response? Because at the denominator it have a function of s plus a certain constant. Because s plus a certain constant, in inverse Laplace you will introduce the exponent part of the equation. So all of this will become natural response. This part will become forced response. Right? So now we'll go further. The next step is of course to do the inverse Laplace transform, but now we still don't evaluate the value of K1, K2, K3 and K4. We just want to evaluate it by inspection. So we know that the inverse Laplace of K1 over S is the constant K1. If we inverse Laplace K2 over S plus 2, it is K2 exponential minus 2t, and the same goes for the two other fractions, plus K3 exponential minus 4t plus K4 exponential minus 5t, right? So now we have the forced response and we have the transient response, right? So we know that we have a transient response which is influenced by exponential minus 2t, minus 4t and minus 5t. So this time response is basically also the solution to differential equation, but without having to go through the differential equation, which is quite complex here to be solved, right? So this one, if we look at the FBD that lead us to this, solving it in order to be able to get this time response is pretty complex. But now we can already find what is the form of the time response without having to do any calculation whatsoever. So of course at the end, if in previous slide we only know that it will be in this form, so it is this form, but at the end, if you want, so this is solution by inspection, so we know that it has a steady state value, it has a transient value, and transient value is depends on all this exponential part. But at the end, if you want to have a precise response, of course you will have to evaluate the value of K1, K2, K3 and K4. And to do so, what you do is you do your trick of solving partial fraction. You do your usual trick of solving partial fraction. So I'll skip through this. So by solving the partial fraction that were in previous slides, you can of course try to look at the slide that I also attached with the lesson. You'll find that K1 is 3 over 40, K2 is minus 1 over 12, K3 is minus 1 over 83, and K4 is 2 over 15. So what we need to do is really only at the end you try to solve the partial fraction. So the only thing that you have to do is basically partial fraction, right? The inverse Laplace, you know what they are. They are exponential minus at, and you already know that there will be a constant which correspond to the forced response. So same goes for here. What you can do next is, we are interested in to do next is of course to plot the graph of the output. So here is the graph of the output plotted using MATLAB. Of course you can, what I suggest you to do is not just, of course, because plot using MATLAB is easy, but the hardest part is to look into that equation and try to evaluate the form of it, the form of the transfer function, the form of the time response. So in order to do so, what you do is to find Ct at t equals to 0 and try to evaluate Ct when t tends toward infinity. So please do that. So now we kind of do this in a reverse order, but what we've seen just now is the generality of it. So it is applied for first order system, second order system, or any n order system. But in particular, now what we're going to concentrate on is first order system. Now that we know how to plot the time response, to evaluate the time response, and then plot the time response of a first order system, there are several criteria of performance related to first order system that we need to understand and we need to know. Because when you design a control system, you need to be able to evaluate the performance criteria of this first order system in order to, for example, make any modification on the value of your parameters if necessary. So first of all, again, what is the order of the system? So what we're going to do now is to generalize a first order system. We know that a first order system is a system with only one poles, right? So we can generalize it. So a first order system can be written in standard form. So this is a standard form that will help you in so please remember this is the standard form of a first order transfer function that will help you in finding the performance criteria. So in a standard form, it is written as A over S plus A. So any first order transfer function can be written as A over S plus A. So we have only one poles at A, right? So if we plot it on S plane, so what we call as S plane, our poles equals to minus A, which is a real value, is not a complex value, so there's nothing on J omega axis. It's equal to minus A, so we can put it at minus A. So here is 0, here is positive part, here is negative part, so it's minus A. So this transfer function can be A, can be any values, right? So it's equals to minus A, and here is what we call the plot of the poles and zeros on S plane, right? So we have one pole. So let's see if we have the transfer function of a first order system in the standard form, what would be the time response solution if we do it using inspection. So using inspection, again, the response is, of course, CS is the multiplication of input with the system. So input, here we have input step is 1 over S multiplied by A over S plus A, and by inspection we know that there is a K1 over S and there is a portion that K2 over S plus A, right? So next, we know that if we have this as output in frequential domain, the input in time domain, which we call the time response, is, of course, it's K1 by inversing Laplace this is equal to K1 plus K2 exponential minus AT. So if you want to know the value of K1 and K2, of course you have you take your value of A and you plug in the value of A and you do the partial fraction in order to find it. So now, for example, let's assume that A is just A. There's no value of A, and if we do the partial fraction with A as the parameters, we find out that K1 equals to 1 and K2 equals to minus 1. So in standard form, right? In standard form, the time response of a first order system, which is written as A over S plus A, the time response can be written as CT equals to 1 minus E exponential minus E minus AT. So time response is CT equals to 1 minus exponential minus AT, right? So this is the time response of a standard or a standard form first order system. So if you have A of a different value, of course you have a time response, different time response with a different A, right? So this is the standard form that you have to remember. If you have any other function of first order that you have, what you need to do is you need to transform it into this standard form, because it will be easier in order for you to find out the time response. Now that we have deduced these properties, in next exercises or next problems that you encounter, if you have a first order system, you can do this property, you can use these properties directly, which is transform it into the standard form and directly write the time response, right, without going through all the steps that we've seen previously. Now in this slide, we're going to look at the characteristic of performance related to the time response. So now, again, the standard form is A over S plus A, and the time response in the standard form is CT equals to 1 minus exponential minus AT. So that if we plot the time response will look like this, right? So we look like this. So it ends at 1 because we have the amplitude of the force response, which is the input is 1, is a step of 1, so it end up at 1. And now we have a curvature here, which is the transient response, which depends on the exponential term, which is what we call also the natural response. So there is several criteria of performance that we can evaluate by looking at the time response. So the criteria are noted here. The first one is what we call time constant. Time constant, right? So basically it shows us how fast that system react, right? And there are other things as well, which is TR, what we call rise time, TS, what we call settling time. Let's look into the definition of each criteria of performance of first order system and how can we evaluate them, this criteria. So the first one is time constant. So what is time constant? Time constant basically is the time that it takes to reach 60% of the final value. So the final value here, for example, is 1, right? Is 1. So time constant is the time that it takes for the system to reach 60% of the output. So it's pretty close to the output, 60% of the output. So if you look now, the steady state response at steady state is 1. 63% of 1 is 6.3. So we have it here. So if we plot at 6.3, if you look at the time, so this is the time as what we call as time constant. So there is a formula for it. What is time constant? Time constant can be calculated if you have the value of your poles A. Remember, our system is written as A over S plus A, and the time response is basically can be calculated as 1 over A. So it can be calculated as 1 over A. So the A is basically it's your poles, right? It's your poles, and TC is time constant is 1 over A. That's why it's very interesting to write your transfer function in frequential domain. I mean, to have our system written as transfer function in frequential domain and to identify the poles, because just by now we can see that just by identifying the poles, you can directly deduce the time constant of a system. So deducting the time constant of a transfer function means you know if the system is fast or the system is slow. For example, if time constant is high, it means here the 63% value will be more towards the right. So the graph will be more like this. So let me draw it. So if for example TC is higher, then we will have more delay in it. So this is, for example, the new TC. If we have different A, then we have different time response, which could delay or which could fasten the response. So just by knowing TC, we know if the system is responsive or is not very responsive, right? So what are the influence? For example, if A is small, it means TC is, if A is small, then TC is high. So the TC tends toward this right side. If TC tends toward this right side, it means the system is less responsive. So now what you can conclude is, if you want the system to become faster, this is a fast system, then the TC is very, very small. In order to make TC very, very small, you have to have a high value of A. So the higher the value of your poles, so the faster your system will be responding, right? So that's for time constant. So there are other parameters as well that are also reflect the responsiveness of the system. It's just a different measurement. For example, here is what we call as rise time. So what is rise time? Rise time is the time that it takes for the system to go from 0.1% of the response to 0.9% of the response. So final value, for example, is final value here is 1. Let me change to a pointer. So final value here is 1. So 0.9% of 1 is 0.9. 0.1% is 0.1 of the output is 0.1. So the difference of time between these two is what we call time a rise time, right? So again, it can be calculated using the value of poles, which shows why is it very important and interesting to know to identify the poles. To find the time response equals to 2.2 over A. It can be calculated as 2.2 over A. The next one is what we call settling time. So what is settling time? Settling time is the time that it takes to reach it's not 21%, it's 98%, to reach close to 2% of the final value. So for example, if final value is 1, let's see, it is the time basically to reach 0.98. So it's this time here is the time to reach nearly the steady state. So it can be calculated as TS equals to 4 over A, right? So there are 3 criteria of performance of a first order system, which you can calculate using your poles. So you need to identify the poles. Time constant is 1 over A, rise time is 2.2 over A, settling time is 4 over A. So here we have several examples. For example, this is an example, easy example. GS, we have a transfer function of first order system written as 50 over S plus 50. So we know that the standard form, so if I can write, the standard form is written as A over S plus A, right? And the time response CT can be written as 1 minus exponential minus AT, right? So we can use these properties, but we have to know what the value of A is. What is the value of A? So here it's easy. Our A here equals to 50. So A equals to 50, and poles. So basically A is not minus 50. A is, I'll cancel this. A equals to 50, but the value of poles is minus 50. Poles is minus 50. A is 50. So we know that we can, if we use this CT is therefore is 1 minus exponential minus A. So minus A is 50t. So CT equals to 1 minus exponential minus 50t. So we get the time response, and you can plot it. Of course, if you want to plot the graph, you can plot it. But even without plotting it, knowing the value of the poles, we can directly find the criteria of performance, which are time constant, rise time, and settling time. So this is easy. Of course, time constant is 1 over A, so it's 1 over 50 second. Rise time is 2.2 over A, so it's 2.2 divided by 50 second, and settling time is 4 over A, 4 over 50 second. So that's how you apply it for a first order system to find their criteria of performance. So here we have a slightly different form of transfer function, right? So now we don't have, if you remember, the standard form is A over S plus A, but now we don't have A over here. We don't have A. The value of here and here are not the same. They are not A. So what you need to do is basically to factorize this so that we can have a similar value here that can be identified as A. So what we can do is factorize the 200. So it's 4 multiplied by 50 over S plus 50. So now our A is this, 50. So again, A is actually 50. It's the same as what we had previously. What we have now is just that the transfer function now is multiplied by a constant 4. Multiplied by a constant 4. So we have the same response, which is 1 minus exponential minus 50t. So the poles is minus 50. Again, poles is minus 50. But it's just multiplied by 4. So in general, we can say that if we have the standard transfer function can be written as, if they are not equals, the equals one is A over S plus A, but it can also be written as K over S plus A. And for transfer function of K over S plus A, the time response is K over A multiplied by 1 minus exponential minus AT. right? So you can use these properties directly. So let's take, so this is an example of it. So for example, if we have this, then K over A is basically 200 divided by 50. This is where we got 4, and the terms inside is 1 minus exponential minus 50t, right? So again, what do we see here? There's an interesting properties here, because why? Knowing that basically knowing that the time response is only depending on the value of the poles, right? All the criteria of performance, be it time constant, settling time, or rise time, depending on the pole. So the value of this criteria of performance are equals, right? Are the same. So what does this for do? So this for, what does it does is basically it increase the amplitude of the steady state. So it just increase the amplitude of steady state, but the times taken to reach it are the same. So if previously, if it were not 200, what we have it right here. But what we do here now is just that we shift it. You shift the steady state to a higher amplitude. But still, we have the, in terms of criteria performance, time constant, rise times, and settling times are the same. So we can also do it by experiment, right? If you don't have a transfer function, so this could also be interesting. So I'll let you look at the slide slowly and steadily. So for example, if you have a system and you don't know what the transfer function is, what we can do is the inverse of it, right? So what we can do is to find TC. If, for example, let's say you have a system. Let's say your system is a spring and a mass system, right? Spring and mass system. You don't know what the value of K is. You don't know what the value of M is. So you cannot write your transfer function. If you cannot write the transfer function, then you cannot deduce your value of poles, right? You don't know what the value of pole. So how do we do this? If you don't know the value of the poles, what we can do is we can do experiment. We do experiment. For example, you take your system, you pull it with a force of a certain force, and then you trace the graph of its displacement, right? You trace the graph of its displacement. Let's say this is the displacements of this mass. Once you have the graph, what you can do is you look at 63% of the steady state value, right? And then you go to the time and you look at the times that you found, and knowing that for first order system that the time TC, the time constant is 1 over A. If you found a value over here, then that means you can find the poles. You can identify the poles of a system that you don't really master by doing an experiment. So for example, let's imagine for this system, it was found that the time constant at 0.63 is 0.13. Therefore, A is 1 over TC, which is equal to 7.7. So we have found the poles A by, this is what we call by experiment, right? And we know that the general solution, if we want to go to the value of K over A, because we know that the general solution is this. If we want to go to the value of K over A, then we can do this, right? Because we know that K over A is the force response, right? And K over A, which is the force response, is equals to, if you look here, is equals to 0.72. And knowing that this is K over A, we can therefore deduce the value is value of K, knowing that the value of A have been found here. So by experiment, we can go back and find our transfer function and our time response properly. Okay, and of course find back the poles. So now if you look at it, now we can write the transfer function even if you don't know the value of the parameters by experiment. So now we know that K have been found to be equal to 5.54 and A equals to 7.7. So the transfer function GS of our first order system is 5.54 over S plus 7.7. So there are multiple example of exercises, so please do them. So for example, this one is exactly like the previous slide. It is easy. So this is the response. So we have come to the end of the lesson this week, the video lecture. I hope that you will study this. I mean, watch the video lecture along with the slide to be able to understand it properly. And then after this, of course, do the quiz that I'm attaching with the lesson material in the Google Classroom. Thank you very much and see you next week.